So a very good evening to everyone. Good morning, good afternoon. All right. So I'm Dr. Chong from the Astro Society of Penang, and tonight we are so honored and fortunate to have our two astronomers, Dr. Koay Jun Yi and Dr. Juan Carlos Algaba Marcos. All right, will be with us to share the discovery of the recent discovery. What was that? 3 days ago, on 12th of May 2022 at Malaysian time 9 p.m., announcement of the second image of the supermassive black hole in the center of our Milky Way galaxy, Sagittarius A star. Of course, the first image was 3 years ago, 2019. This Dr. Kevin Koay also came to Penang to give the talk also. Right? So this is the second one. We're all very excited. So we're going to have a Q&A session with Dr. Kevin Koay and Dr. Juan Carlos Algaba Marcos. We've done that. So our ASP member will be on the same Google Meet with us. They can pose their question, and you can even see them and interact with them and answer. And then later on, we'll read. We see in our society's Facebook and this what we call YouTube channel, the question posed by the non-members will be there. Right? So maybe when it starts, maybe Dr. Kevin Koay and Dr. Juan Carlos Algaba Marcos will have the opening statement to make the general comment, and then we post them the specific question. But before that, background. So Dr. Koay Jun Yi is from the Academia Sinica, which is an Institute of Astronomy, Astrophysics in Taipei, Taiwan. Okay, of course, Dr. Kevin Koay originally from Penang School, and he got his he's actually support astronomer in ASIAA on GLT and VLBI, Greenland Telescope, and very long baseline interferometry. So this is what part of radio astronomy. And he got his PhD from International Centre for Radio Astronomy Research, Curtin University, Perth, Australia. Right? And we now know that the EHT team, Event Horizon Telescope team, that got this second image of the black hole, has now 300 astronauts around the world. Whereas in 2019, the first image was 200 astronauts. Now it's 300. And for 80 institutions and 20 countries. Of course, the institutions are, for example, ASIAA in Taiwan and Universiti Malaya, where Dr. Juan Carlos is. All right. And then the first discovery was in 10 April 2019. First image, the recent one was 12th of May 2022. Dr. Juan Carlos Algaba Marcos is a senior lecturer in the Radio Cosmology Laboratory in the Department of Physics, Faculty of Science. Remember, Universiti Malaya still follow the British system. Most of the Asian universities use School of Physics, but this is Faculty of Science, Department of Physics. And he got his PhD in physics from University College of Cork Island. All right. So both Dr. Kevin Koay and Dr. Juan Carlos Algaba Marcos are in the EHT team, Event Horizon Telescope. It's a wave of the future. All right. So this is our short wavelength radio astronomy. So before we pose our question, so this is a Q&A session. So before we pose our question, both Dr. Kevin Koay and Dr. Juan Carlos Algaba Marcos can make the opening statement before we ask them the specific question. Okay. So go ahead. We are so honored to have both of you. Okay. Kevin. Yeah.
I think Juan Carlos, you go ahead with the presentation.
Yeah. Sure. Go ahead.
Really? Okay. So then I would like to share the screen. And let me just check if everything is okay. Okay, the screen should be full now. Is that correct?
Clear, very nice. Thank you. Can see.
Okay, so this is going to be a small, short introduction, I hope, just to give a bit of a background, because basically, as it was mentioned in the introduction, this is the second image of a black hole that is produced by the Event Horizon Telescope. You probably remember about 3 years ago, the image of M87 that was in many newspapers, making not only just inside, but in the cover, in the front page of many newspapers. This is also the case today. And the question is, we have been discussing about the Event Horizon Telescope. What is the Event Horizon Telescope? Well, you know that normally when we observe in the sky, what we need is to observe as tiny details as possible. We need to observe better and better resolution. And for that, some of the solutions that we have is try to make the telescopes bigger. The bigger the telescope is, then the smaller detail that we can observe. Of course, this also depends on what is the frequency that we are observing. Since radio frequencies are typically 1,000 times smaller than optical frequencies, that means that we need to construct a telescope that is 1,000 times larger to be able to have the same resolution as we would have with an optical telescope. For comparison, if we want to have a radio telescope that can observe as small details as we can with the eye, of course, the eye will be like 3 millimeters, the pupil, we need to build a telescope that will be about 100 meters, something like that, or 10 meters. What is the problem? We can try to build telescopes that are very big and bigger and bigger and bigger, but eventually what happens is that we are becoming into technological challenges, and at some point we cannot make telescopes as large as that. This will be the example of the Green Bank 300 feet antenna. This will be a picture of a sunny, beautiful day when it started operating, and this is a picture of what happened afterwards. Basically, this collapses, and this is an indication that we cannot keep going and keep constructing bigger telescopes. What do we do then? Well, the solution is using interferometry as very long baseline interferometry techniques. And the basic idea is when we think about the telescope, the main thing that we are doing is collecting the rays of light that come from basically very far away and try to focus them in what we call the focus. Well, we can do this, for example, with a mirror or with a lens or with a parabolic surface in the case of a radio telescope. But if the telescope will be too large, something else that we can do would be, instead of having a super large parabolic surface, we can just make little telescopes or little surface there. And then since they are little, we can just move away and put it somewhere else. Of course, when we are putting the little surfaces or little telescopes in different locations, the rays of light will have some sort of additional path, which we have to correct. When we do that, we can set the signal and we can create a virtual focus. Basically, we are doing the same thing as before. We are just letting the ray go and we are directing the rays to a focus, whether it is a real focus or a focus on a computer or something like that. It's not a big difference. We are still trying to catch the same image. The big idea here is that now, instead of having a big surface, like a parabolic surface or a big mirror or a big lens, we can have tiny telescopes. And the only thing that matters is how far we can put them away. For example, for the case of the EHT, what we are doing is putting the telescopes as far as we can do on Earth. In this sense, creating a radio telescope that is as large as Earth, without obviously needing to construct a surface that covers the whole planet. And with this kind of telescope is how we have obtained the images of the black hole. Of course, the Event Horizon Telescope is not the telescope itself. There is a huge collaboration, a huge amount of power, a huge amount of people working behind it, a good number of institutions. So there is a lot of collaborations there. This would be the EHT board. What are the institutions that are part of the EHT as part of the board? But this is not only it. If you look at what are the countries, the locations involved in it, there is a map, and you can see each point here will be one different institution, one different location, and you can see that they are everywhere in the world. They are in Asia, in Europe, in Africa, America, and we can zoom in and look at the East and Southeast Asia region, and you can see that there is a point there, a very nice point that is just located in Malaysia. Of course, this is some of the institutions. In one of the papers that was published, you can see that there are all the way to 176 institutions. And you can see that Department of Physics, Faculty of Science in Malaysia is one of them. Of course, Academy Sinica is another. I just wanted to focus on the Malaysian side here. Sorry about this, Kevin. And of course, this is not only the institution, Universiti Malaya, that is supporting this effort, but we also got acknowledgements in the paper from the Fundamental Research Grant Scheme from the Higher Education Ministry of Malaysia. Of course, as you know, like the Malaysian contribution can be said in the terms of Kevin, a Malaysian, and myself, who am not a Malaysian, but at least I'm working in Malaysia. So, of course, as I mentioned, we have support from Universiti Malaya and the Ministry of Higher Education. And this is the image of the black hole in our galaxy that we obtained. So now the question, of course, is, well, what is so interesting about this image? What should we care about it, or what should be the items that we will considering about this image? So I would summarize maybe the keys that I would like you to take home into three different items or three different perks. Number one, well, in some sense, it's interesting because it's the black hole, not in a different galaxy like MET7 3 years ago, but this is our own galaxy, our own black hole at home. So I think only by itself, that's something quite interesting about that. Well, this is something that's much closer, that is part of our own galaxy. So in some sense, it's explaining the place where we live. Perk number two, well, the inclination angle of this black hole, or basically what is the axis of rotation, it may be funny. As we have made some models, and it is interesting that it is not really following the same rotation axis of the galaxy. It seems, or it may be the case, that it's following another axis. And of course, this may have implications of why is that, and what is the history of the galaxy and the black hole that made it happen. And a third perk, it would be that size doesn't really matter in this realm. I will discuss about this, but basically the idea is now we have two samples. We have a black hole that is millions of solar masses. We have a black hole that is billions of solar masses, 1,000 times more, and yet they look basically like a donut, both of them. So this is really telling us that the physics behind it is basically the same. So this is an image of basically the black hole in the context of our own galaxy. This would be how we can see the sky basically from the South Pole. And we have different zooms into what is the galactic center until we can reach the black hole Sagittarius A star. So just to put the context of where in our neighborhood, in our home, this black hole is located. And if we want to put this in context of MET7, this will be an image of the black hole in MET7. And since our own black hole, Sagittarius A star, is 1,000 times smaller, of course, the size is going to be much smaller. And you can see here comparison of the different sizes of MET7 star and Sagittarius A star. Why? That's one of the questions that you may ask. Why we presented first the black hole in MET7 and not the black hole in our own galaxy? Well, you may think the black hole in MET7 is much farther away. It's also much bigger. So when we look at the sky, they more or less look like the same apparent size. But the problem is that when we're looking at our own black hole, we have to look through all the material, all the gas, all the dust from our own galaxy. So this is going to be causing a lot of distortion. This is going to be causing effects, refraction, distortion, and of course we have to take into account these effects if we want to really make sure that what we're observing is really what it is. And the other concern is that since this black hole in our galaxy is much smaller, the dynamics can be much faster. That means that even if all the material goes around the black hole at the same speed, since it is faster, it takes much less time to actually go one time around it. So since it's more dynamic, it changes much faster, then this can be a problem when you want to observe it. It's a bit like if you want to make a long shot picture, but something is moving, then your image is going to be blurry. You have to be quick enough to take the picture before it moves too much, or you have to apply some tools to take this into account. And this is what we have done with the MET7 and Sagittarius A star. Here is an example, a picture that kind of shows what will be the difference. MET7 is bigger, MET7 is not that quick, so we want to take an image of it. It would look not so bad. But when we want to make a picture of Sagittarius A star, it's basically like trying to take a picture of a dog chasing its tail. It's more dynamic. Not only that, but also taking the picture behind the rain in a foggy environment. So of course, we had to put all these elements in the game. And this is why taking a proper, reliable picture of Sagittarius A star took more time than for the case of M87. Of course, one of the perks that I was mentioning before is that size apparently doesn't matter for this case. And this is something that you may think it's obvious, but it is not. When you look into normal everyday life examples, you may think, you think about an elephant or an ant, and look, for example, at the size of the legs. The legs of an ant are much thinner than the legs of an elephant. And this is because of physical reasons. There is a pressure involved there is a weight, and the pressure goes at the surface, whereas the weight goes at the volume. So the larger you go, then the more weight you have to support, you have to make it thicker. You cannot just zoom in the animal, you have to take into account these things. So in that sense, how big the animal is going to have strong implications on how it looks like. Same thing when you look at a rock. Typically, you look at a small rock, let's say small in the context of astronomy, and it will have some peculiarities. It may have random shapes, it may be sharp, it may not be. But when you look at rocks big enough, like planets, typically they will try to have this kind of rounded face. So again, the size is very important there because it's telling you what are the effects that we have to take into account. But when we go to the sizes of black holes, then the thing that is going to be there is going to be basically gravity. So that's the only thing that we have to consider and take into account. And when we make the studies, we expect that size is not really going to be a matter of importance. Therefore, when we look at both Sagittarius A star and M87, we always expect to see donuts. As somebody was mentioning some days ago, the universe is basically going to be full of donuts. Because I don't care if the size is 1,000,000 solar masses, 1,000,000,000 solar masses, something in between, it's all donuts there. And the last perk that I was mentioning would be the inclination angle. You can think about the disk, you can think about something in the center, and you may think that everything should rotate in the same way, but maybe this is not the case. And this is again something that we may have to think about. Why this happened, what is the scenario, what is the history, what is going around there. So those are some of the perks, ideas, investigation, research that, of course, is going to be open and is one of the topics or some of the ideas that we want to study when we are observing the black holes. So I suppose I can stop here. I have some other slides prepared in case some people may have some questions, but I don't want to steal more time. So please, you can go ahead.
Thank you, Dr. Juan Carlos Algaba. Maybe, Kevin, you have some words? Your statement before we ask the question?
Yeah, I don't have anything much to add. I think Juan Carlos gave a very excellent, overview of the result and also the EHT. Probably maybe one thing I will add is just to say that what makes Sagittarius A star unique? I mean, now we have two black holes that look very similar at the scale of the event horizon, right? But outside of the event horizon, they actually are very, very different, right? I mean, M87, you have this huge jet that is coming out, and that is interacting with the whole galaxy, and stopping new stars from forming and things like that. But in Sagittarius A star, we don't see any jet as far as we know. Especially at this point in time in the history of the Milky Way, there's no evidence of any jet that we have so far right now. So they are very, very different, in terms of what's happening far outside. But in the center, they look the same. So trying to understand what makes these two black holes so different. The way they are feeding the gas or the way that they are interacting with their environment is very interesting. Something we are looking into. And also one thing is, M87 black hole is a very rare class. It's a super huge. I think probably one of the biggest that we know. Yeah. And they're actually very rare. Whereas the Sagittarius black hole is a much smaller ones. They are much more abundant, and they are more of a typical kind of black hole that we would expect to find in the universe. They're a more common kind of black hole that is not so active. Whereas the more active one, the ones we call like active galactic nuclei, they are just a small fraction of supermassive black holes in the universe. So Emily, studying Sagittarius is going to give us a look into something that is some of the more regular and common nature of black holes in the universe. I mean, yeah, probably that's the only thing they want to add, in terms of the differences between the two that we are seeing. Yeah. So yes, I think you can go and move ahead to the questions.
Yeah. So thank you very much, Dr. Kevin Pei, for making your statement. So now we open the Q&A session to our ASP members. I see some names here. So anyone want to ask question, go ahead. Suresh, you got any question? Suresh, are you there? On your microphone?
Yeah, I'm here. I'm just listening. I have no questions yet.
Okay. So Bunwei, any question? Our USM student, Bunwei?
I also just listening.
Yeah.
Yeah, till now still no question.
So maybe I can ask both Dr. Juan Carlos Algaba and this Kevin question is, so we know that you all are working at 1.3 millimeter wavelength, and Dr. Juan Carlos mentioned just now, the bigger the telescope, the better the resolution. Another way is the shorter the wavelength, the better the resolution. So what are the technical challenges if you go at shorter wavelength to go sub-millimeter, below 1 millimeter? Is it possible to do or not? And what are the challenges? Shorter wavelength, better resolution. Of course, technical challenges. Yeah. What is the technical challenge?
Maybe Kevin can.
Should I?
This question?
Yeah, okay.
Yeah.
So maybe I'll answer this first. So actually, a lot of the telescopes that we are using now, some of them, for example, like ALMA,
Already.
the Greenland telescope, and I think most of them, I think 8 or 9 of them already have capability to observe at 345 gigahertz. And ALMA even higher, because they have a much better sight, 600, 700, I mean almost 700 gigahertz. But I think, so actually the last, I mean 2021, we already did an observational test with about 4 or 5 of the EHT telescopes to try to observe at 345 gigahertz. So we did a test during that time, and next year onwards, they're actually allowing proposals to observe with EHT 345 gigahertz already. So next year, 2022, we will be observing M87 and Sagittarius A star with 345 gigahertz, which will give us slightly better resolution. But of course, the target, if we want in the future, we are aiming for even 660 gigahertz. So the GLT and all this, the site that we have in GLT currently is on the ground level, but we want to move it up the mountain so that we in Greenland, so that we can actually observe. We have better weather to observe at 660 gigahertz. And with 660 gigahertz, we have even higher resolution, because currently at 230 gigahertz, or like you say, 1 millimeter, right? We can only see Sagittarius A star and M87. These are the two that we know so far that we can resolve the shadow. Right, by 660, I think we can resolve a few more black holes. I can't remember which one. Could it be Centaurus A or a few other ones that we might actually be able to resolve? But currently, most of the other telescopes besides ALMA don't have that capability to observe at 660 gigahertz yet. Yeah.
So in a sense, I would say that the fun is just beginning. You got 2 black holes, and then you can get better resolution of even the 2 existing black holes, but possibly many more black holes in future. So just the beginning only. So Eric, any question? Eric? So Michael, go ahead. Yeah, anyone? Kevin?
So maybe Juan, your turn.
Anyone?
All right, okay. So basically in the observations of 2017, there were 8 telescopes as part of the Event Horizon telescope. But of course, the more telescopes, the merrier. We have, different things. We're going to have more surface to capture the waves. So that means that we are going to have more sensitivity to observe more details of more thinner and dimmer details of whatever we are observing, 7 Sagittarius star. And that also means that since we are connecting different telescopes, the ways we can connect them are going to be increasing a lot, which when we are calibrating data, is going to be super nice to have that. We had 8 telescopes in 2017. Then 2018, correct me Kevin if I'm wrong, Greenland telescope joined, right? And then in latest observations, we had 2 more telescopes. One was Kirkpic from University of Arizona and Noema telescope in France. So now we are having 11 telescopes observing, and of course, this is principally going to make it much better observations, much better quality, much better sensitivity to what we can observe. Of course, as projects, we want to do polarization observations. We want to check how the magnetic fields behave, not only on 7, but Sagittarius A star and other targets. We are also observing different kind of galaxies, always active, always thinking there is a supermassive black hole there. And even if we cannot resolve it yet, still we can try to figure out what is really happening surrounding the black hole, or how the jet that Kevin was mentioning for the case of M87, how it is formed, where is the footprint, if it is created because of the accretion disk around the black hole, is it created because the rotation of the black hole? This is things that we are going to be achieving, not only with the addition of telescopes, but making higher frequencies and considering what we call the next generation event horizon telescope. I suppose maybe Kevin wants to add something here.
Michael, more question?
Sorry, just now I forgot to turn on my microphone for the audience. So I repeat, the answer just now is to the question by Dr. Johnson on whether there will be more telescope added. Then next we have another question from Facebook from Hermes Francis. So he's wondering how big is the data of the picture in terms of gigabytes. So remember the previous M87 is always we have shown the picture with all these hard disks and all that. So what about this time? Do we have more data or way more or almost the same? Since we are dealing with more telescope, right?
Yeah, so actually the data, I mean, if you're talking about the image itself is actually just a few megabytes, right? I think I can't remember, like the image is just a few megabytes. But when we are doing the observations, right? The observations, the data, that is a lot. Now the reason is because we want to have very high sensitivity. So for these radio telescopes, we want to have high sensitivity. We observe at a very large bandwidth, right? The bigger your bandwidth, the higher the sensitivity you can observe. You can integrate over the full range of frequency. So in 2017, we observed at a bandwidth of about, I think, 2 gigahertz. I think each 2 bands, right? Each band is like 1 gigahertz each, I think. But from 2018 onwards, the bandwidth is now like, I think total is about 4 gigahertz, if I'm not mistaken. So 4 gigahertz, and then we're also talking about we have to record at very short time scales, right? Because for VLBI, I mean for interferometry to work, you need to sample the same exact wavefront of the wave, electromagnetic wave. So you have to do your measurements at very, very short time scales, okay, and have very accurate, clocks to measure this so that we can adjust the time so that we are sampling a very short time, especially for these high frequency observations, right? And because we cannot observe at too long time scales, because then you have the atmosphere and all these things, messing things up. Okay, so everything has to be short time scales, so you can adjust your clocks, adjust the timing of your like Juan Carlos was mentioning, that you're trying to do a virtual focus position, and you have to shift your time delays. So because of that, the data actually we record is quite a lot. So the recorders that we use at each telescope records about, I think, 64 gigabits per second now for each station, right? You can imagine 1 second, 64 gigabits, right? At one station, Previously it was 8 stations, now it's 11, right?
Mm-hmm.
So you can imagine how much data there is, because typically we observe like about one campaign, like 1 year we'll observe about 6 days of observations, 11 different telescopes. So typically when you come up with the full data set, when it arrives, it's usually on the order of petabytes, which is a few thousand terabytes of data. And that data gets shipped to the correlator, which processes the data down to about 3 terabytes, a few terabytes, okay? So basically they're just combining the signals from different pairs of telescopes, right, into a few terabytes. And then we will process the data even more. So that is the main thing that I'm working on now, processing the data, doing the calibration, so that you can average much more data together in frequency and in time. Okay, so we can shift, all the atmospheric effects and everything, the gains, calibration, so that we can average all the data into smaller chunks into just a few megabytes, and then after that, we can use that to produce the images. Yeah.
Yeah, I just checked the M87 one was 5 petabytes total.
Yeah. So I mean, it's the same. I think that the 2017 data contains all the targets. So everything that we observed in 2017, I think total was like a few petabytes of data.
Okay,
so because when we observe everything together, like on the same, typically on the same day, and usually a few targets together. Yeah.
Allow me to make my own observation of VLBI. I'm always impressed by VLBI. It's mind-boggling, because I used to tell my USM student astronomy class that, do you know that optical telescope has such a resolution? They are trying optical interferometry, not so successful. But VLBI using radio astronomy is the highest resolution astronomy in the world. For example, your what they call Sgr A star is about 51 micro arcsecond. The one in M87 is even smaller. So that means the resolution is even better than optical telescope. So I'm very impressed, and the whole Earth's surface is like a radio telescope. Very impressive, mind-boggling. Yeah.
Okay, so there's another question from Jan Hao. So, hi doctor, from the previous M87 image, we can see the left side of the ring brighter, indicating a Doppler boosting, and the other side dimmer with deboosting. How about the ring this time with 3 spots in the ring seen?
So I suppose it's my turn to answer. Okay.
I think
So
Carlos, I think you have some slides that show that, or
I don't think I have slides to show this particular answer. Oh, maybe I have. Yeah. So then let me. Yeah, I can try to share this. There was a beautiful movie that was made by the Event Horizon Telescope, but I have just one picture. So the basic idea about this, I suppose you can see my screen now. I can just go full screen if you want. The basic idea is very much related with what I was mentioning before of both the dynamical time, the dynamic time scales for Sagittarius A star compared with M87, and also the, let's say, atmosphere, the conditions in between, like there will be a lot of gas and dust, stars. We are looking basically through the plane of the galaxy when looking at Sagittarius A star. So in some sense, it will be quite similar than considering we are looking at some stones, but we are looking for a long time so that the conditions are changing. So at some point, let's say we are taking pictures of there is going to be cloudy, and then it's going to be less cloudy, and then we can see the stones, or sometimes there is going to be all the fog coming by and we don't really see much of the stones. So all these kind of different situations, all these different pictures that we see are going to be happening when we are observing the time scales. In the case of M87, it's going to be the time we need to take a picture of M87 is going to be much shorter in comparison to these time scales. So we are not going to observe too many changes. But for Sagittarius A star, we are going to observe a plethora of changes while we are observing. So at the end of the day, what we are doing is kind of try to take an average of what we think we see within all these changes. And the image that we are showing is basically not an image at this time or at that particular dynamic event. It's more like an average image of what has happened. Just to keep in mind, typical scales in Sagittarius A star will be of the order of minutes. And we were observing for hours. So of course, when we saw the image, it's going to be really long exposure of something that is moving, and the result is going to be an average. If there was a spot of a bright feature or some effect that was moving while we were observing, of course, this is also going to be average. So in that sense, what happened is that we were checking and rechecking and making different calibrations and making different images and checking which parameters will get the best image. And at the end of the day, we were obtaining, I don't think I had the image here, but we were obtaining, let me just go back to the image.
I have that slide, I think, if you want me to show.
The video?
No, not the video, but the picture with the 4 panels underneath.
Okay, you can show it. Basically, we had the different options when we were taking the average. So I stopped sharing the screen and you can share that one.
You can see my full screen. Yeah, so basically this one. Oops. Yeah, this picture, if you look at if you are interested, you can look at our papers that were published in the Astrophysical Journal letters. Right, this is the picture that we use in the paper. Right, and wait, can you hear me? Right, okay.
Can hear you.
Yes, yes. So basically, we run through the imaging using different kinds of software, different kinds of with different kinds of parameters and all that. And we find that we were getting different kinds of images. Unlike M87, where all our software, all our programs, and all our parameters, we got the similar ring, and the bottom is the brighter region, right? But for Sagittarius A star, we were getting different kinds of images. You know, some of them, the brightest spot is maybe here, right, in the southwest, and here maybe in the north, and here maybe in the east, where is the brightest part. So different parameters and different softwares and everything were kind of giving different kind of images, right? And there are some images that actually don't even show a ring at all, you know, and this is a small fraction of the images, right? So this final image that we show to the public is actually, in the end, an average of all our, I think it produced millions of images from all the different software, different parameters. Yeah, so like I said, Sagittarius A star is a bit more challenging compared to M87, where we were getting consistent, you know, bright spot at the underneath, at the bottom. So we are quite confident that that is what M87 should look like. Whereas for Sagittarius star, we are still not very sure like which of these images is the correct one. And you can see the most of them, the bright spot is up here and maybe just a little bit less. So this kind of bar chart here shows you the kind of the number of images which have this kind of structure, the number of images that have this kind of structure, and this one. And a small fraction don't have this ring in the middle. But even then, you know, especially for all the one with the ring, right, all of them, the size we get is always 50 micro arc seconds. And even this one, where sometimes we see like a double structure, the distance is always like about 50 micro arc seconds, you know. And so yeah, that's why we had these 3 blobs here. It's actually just an average of all the images that we have. And it could be something to do with the time variation, but we are not 100% sure. It could be it's just some of the imaging, you know, artifacts or things like that as well. But yeah, so we are still looking into this, and we need more studies, I think.
Mm-hmm.
Yeah.
Any more questions, Michael?
Yeah, sure. Wait, there's another question from his name is in Tamil. I cannot read.
I have a question. Actually, in 2019 came up, we downloaded the 6 papers. 6 papers we went through. Of course, the recent one also got 6 papers, but we are still going through. So in 2019, what I understand is you have 8 telescopes, radio telescopes. All of these telescopes around the world are imaging M87 star at the same time. Not different day, no. So let's say at a certain time chosen, all the 8 telescopes must be observing M87. So you make sure that the weather in these 8 locations will be suitable for observation. If let's say the weather in half of the telescope 4 are not good, you cannot have a good result. So every one of them must be working at the same time. Okay, of course, the atomic clock are all synchronized, but the weather must be allow you all to do it all. So that's not easy, you know. But from Greenland to South Pole, Mexico, Spain, and Hawaii, you cannot have perfect weather all the time. So just the weather management is a problem. I would think so lah. That's why I guess it to be lah. Not easy, you know. Not easy.
Okay, so there's
yeah, it's actually. Oh, sorry.
Yeah, you can continue. Continue first.
Yeah, actually, it's quite stressful. Yeah, especially because I mean, being involved with the observations, we actually have a window. Usually, the telescopes they give, like ALMA, for example, the big telescopes, they give us a window of about 10 days.
Yeah.
And within the 10 days, we have 5 days of observations. Okay. So every day, what we will do is like a few hours before the scheduled start of observations, we'll have a meeting, call, a telecon, to call for either a go or no go.
Yeah.
So they will assess the weather at all the different sites, at the readiness of every site. Because sometimes it's not just weather, it's the technical issues. This telescope, suddenly there's a problem with the atomic clock or the maser or something, or whether this telescope some issue with the receiver or something, or network down or whatever. So every day, just a few hours before start, you have a call, telecon, every station ready, go. Should we go today or not go today? And there's a committee usually it's based in Haystack, in MIT or in Harvard, who will make a decision, because sometimes it's very hard to make decisions. For example, do we go because this site is bad weather, the other sites the weather is okay?
Yes.
Should we wait another day? The next day the weather might even worse. Maybe 2 telescopes you can't observe. So sometimes they have to make hard decisions. And sometimes, for example, different targets, different telescopes are critical. For example, like Sagittarius A star, you don't have to think about Greenland telescope, because Greenland you cannot observe Sagittarius A star. It's too far in the south, right? And then for M87, it's too far in the north, so the South Pole telescope cannot observe at all.
Yeah.
So you have to consider all these things, and so which source to observe, when and how, they'll have to make a decision, and sometimes it's quite tough, and they have to look at weather predictions in the next few days, and do they expect the weather to be getting better, and all that. So yeah, so it's quite a very interesting experience when you're there, every day deciding whether should we go or no go. Yeah.
I would add to this that even the window that we have, it's not given by chance. Like there is a reason why we observe mostly like once per year on a particular time of the year in April. It's because that's the time in which we think is the best chance for all the telescopes to have good or reasonable weather for this. Definitely, we do not want to observe in October or November when we know that chances are very low. We want to select a window where we think that the weather is going to be the best as possible for telescopes, and later on still like deal with the real weather situation every day.
Yeah. And actually, interestingly, the reason that the observations are always around March or April is because of the seasons. I mean, in summer it's very difficult to observe because you have mostly the sun is up, then the sun messes up the atmosphere and all these things. So usually winter is the best time for observations for millimeter wavelength. Winter is the best time, but of course winter in the northern hemisphere means summer in the southern hemisphere, right? And opposite, and the other way, right? So in between, the transition between winter and summer, that is the best time for all the telescopes in both the northern and the southern hemisphere. It's not the best, but it's kind of optimized, somewhere in the middle between the middle of summer and winter transition between the northern and the southern hemisphere. So usually March and April is like one of the best time to do the observations. Yeah.
And I read in the research paper that processing the data is a big issue. For example, you have collected the hard disk from all over the telescope, but the telescope from this Antarctica delayed because it seems the flight is what they call delayed for so many months, the winter months, harsh conditions. So they are delayed by the data from Antarctica, South Pole telescope. So all these issues are delayed. Not easy, to run it. All kinds of issues. Yeah.
Okay, let me continue with the other question.
So another thing is, I followed also, of course, the announcement in Universiti Malaya in 12th of May in Taiwan. I also followed the one by National Science Foundation in the United States. So the American astronomer mentioned that they have also been looking at the active galactic nuclei. So that means there are some possible candidates they are looking at for the future. So we see which is the next one to do. But for me, I would say that, of course, we know it's not easy. In the Milky Way itself, there are millions of stellar black holes. Much smaller, but in our own backyard, maybe not too far from the Earth. So we hope one day the technology of EHT is good enough you can even image the stellar black hole. Then there will be the whole door is open. There will be a lot of black hole image obtained. But stellar black hole, not easy because they're much smaller. What we are talking now is a supermassive black hole of millions of stars size or billions of stars, right? So there's another big thing called stellar black hole. We have not touched that yet. There's a big market for the future. Yeah.
Okay, let me continue with the other questions. So this one, I think his name is in Tamil, so I cannot read. Okay. So how long does it take to get this result of pictures?
Okay.
I think just now, Kevin, you mentioned that all the observation is done at the same time. I mean, the M87 and the Sagittarius A both are observed at the same time.
Yes, so the both of the ones that we have published so far, that means the results from 3 days ago of Sagittarius A star was observed in April 2017, and the M87 one that we released in 2019 was actually observed in 2017. Within the same 5 days, we observed both of these, and a few other active galactic nuclei that, as Dr. Chong mentioned, a few of them are actually published already. We observed 3C279 and also Centaurus A, and those were published, I think, last year or 2 years ago. Yeah, and there are also a few other active galactic nuclei that we observed as well, like OJ287 or 287, right? Which is a candidate for a binary supermassive black hole, right? So that one we are still working on. It's also from 2017, but we also, later we observed in 2018, 2021 as well. So we are also working on that data now. Yeah, Juan, you got anything you want to add?
So the reason we published the M87 first is because of the simplicity of the processing, or any reason?
Simplicity. It was definitely easier than Sagittarius A star, but that was basically the main reason. It was much easier than Sagittarius A star.
Okay, so we have another question from Astronomy Club HSBM. I would like to ask, will this event occur anytime soon again that will shock the world, and in what way does it affect us? I guess maybe he means another announcement on black hole.
Which is the coming candidate. Very certain they will do it. Yeah. The image.
Juan, your answer, or
Maybe you can go.
coming announcement? Well, I guess what we're working next, for example, like we say, is the 2018 data with the Greenland telescope, which hopefully will give us something nicer, because with an additional telescope, we are filling in more information on this virtual telescope that we have. But I think what will be more interesting is actually the 2021 data, where we have 11 telescopes. Yes. Right? Because, for example, one of the main reasons the Sagittarius A star, we cannot get very, consistent images, or whether, like you say, it's very blurry and there's blobs everywhere. We're not sure if they're real or not. It's much more challenging, right? And that's because we need to do a long exposure, right? We need to integrate. You need to use the Earth's movement, rotation for over a long period to be able to fill in all the gaps, in this virtual telescope that we have, right? But with more telescope, with more stations, you can fill in the gaps a bit faster, so you don't need to, what we call, you can get a much shorter snapshot images, better snapshot image, okay, instead of an average image. Of course, with extra 3, it's not as good yet. But in the future, there is plans for, like the next generation Event Horizon Telescope, which plans to put many more stations and all that to, hopefully get snapshot images, good coverage of this virtual telescope that we have. And then which will help us maybe not just produce, like an average image of Sagittarius A star, but maybe a movie of, Sagittarius A star. But that will probably be, maybe 20 years from now. Yeah.
Okay, so another related question: will we be expecting the polarization image soon?
The polarization emission?
Yes.
Of course. We had all the tools and all the development to understand how we can work with the polarization for M87. Of course, there was also plenty of challenges on how we really need to calibrate all the telescopes all down to the detail in order to make sure how we can trust the polarization for M87. But now, basically, we had the tools and we had the understanding on how we can work with polarization for all the targets. And of course, Sagittarius A star is one of them. We are working now in obtaining the polarization for Sagittarius A star. And of course, this is also going to be giving us information about how the magnetic fields work around the black hole, and what will be the implications for the environment. So there is many things that we will be able to say for the polarization of Sagittarius A star. So I would say that this is going to be like probably the next maybe in the next papers or the next ideas. So of course, stay tuned for this one.
Okay, so
Yeah, Juan Carlos is actually one of the main experts in polarization. He's been working on polarization for a long time, so that's one of his expertise. So if you have any polarization questions, please ask him.
Okay, so another question from Muhammad Ridha. Is Sagittarius A star is oriented face onto our galaxy disk? Actually, myself, when I look at the M87, it looks more round than the Sagittarius A star.
So, yeah, maybe I just quickly share my screen again. Okay, so maybe I'll talk about the second question first, right? About whether M87 is more round or Sagittarius A star is more round. So this was a slide that we were presenting during the Taiwan press conference. So it's in Chinese. Sorry for that. I mean, I also can't read Chinese. But one thing you will see is that actually whether it's round or not, actually the photon ring, right? We expect should always be round. Right? The photon ring, because I mean the gravity, it should be a circle if it's really a photon ring, right? But in the image, so this is simulated images of what we expect. Sagittarius star might look like the photon ring, and the accretion of the gas and everything will look like. Okay, it should be circular. Okay, if you follow, the photon ring should be circular. But sometimes the image, after you process it, right, when it's observed by the EHT, put in noise and everything, it can look non-circular. Like this looks non-circular, right? And that's because there's also additional emission coming from around and all this, which because of our resolution is not as sharp as this, so we can still see sometimes the resulting image actually is non-circular, right? So this is probably what's happening in Sagittarius A star, where there's this illusion that maybe it looks a bit more like an oval rather than round compared to like M87, right? And some people think this maybe means it's maybe tilted a little bit, but actually it's not, right? You can also maybe draw a kind of circle here as well. So the shape maybe sometimes could be just because there's extra emission outside here. Okay. And regarding where it's facing, I think so far, based on all the models that we have, right? I think this was they had millions of theoretical models and simulations, doing all the GRMHD, they call it general relativistic hydrodynamics. Means they include hydrodynamics, include general relativity and magnetism and everything inside their simulations, right? To try to find out which of the models best match our observation of Sagittarius A star. And finally, after filtering through all the different models and with different inclination and different accretion rate and different black hole spin and all those kind of things, there's only a very few models that actually survive. Okay, and the ones that survive, I think, if I remember correctly, tend to be the one that is face on. That means we are observing it face on instead of edge on. So I'm not involved in a lot of the theoretical aspects of the work. But that is my understanding from this. So I don't know if Juan, if that is correct, anything you want to correct or explain?
Well, I'm in the same situation. I'm not an expert of the theory either, but I suppose that's basically how it is. Like, you make the simulations, you check which parameters match what we observe, considering, of course, that we have limitations in the resolution and how things move and all these sort of things. And this is the parameters that seem to be more in agreement with what we observe. Of course, as I was mentioning at the beginning, it seems that is the case. And so most of the models are indicating that the black hole may be face on. But as far as I remember, there were other models that would still be possible with different configuration. There will be a minority, but again, we need more, as we say all the time, like we need more data to make sure that this is really the case. But so far, most of the models seem to indicate that the black hole will be like face on.
So by
Yeah.
phase on,
One-
do we
one-
mean we're
one-
looking at the pole of the spin?
Yes. And there have been, I know papers before, there have people who have claimed that maybe there is a jet that is actually facing towards us from Sagittarius A star. We don't know. I haven't read those papers, but I've heard that there were such papers before. And maybe just to add, that there is a lot of misconception that people think that the axis of spin of the black hole tends to be same as the axis of the galaxy, So they assume that because we are, looking through the axis of the Milky Way galaxy, we are looking through the plane of the Milky Way galaxy, that we expect the black hole to be edge on. That means the pole will be perpendicular to us, right? Because they expect that the black hole should be spinning in the same axis as the Milky Way axis. But actually, this is not the case, especially when we study a lot of quasars and active galactic nuclei and all these supermassive black holes. We see sometimes a lot of cases the jets, because the jets can tell, is one of the few ways we can tell the spin, the axis of the black hole, right, are not always aligned perpendicular to the axis of the galaxy. So sometimes the what's happening in the center at the black hole, the axis is not necessarily the same as what's happening outside in the plane, of the galaxy itself. Yeah, that's one misconception we find people always tend to have. Yeah.
Kevin, earlier you mentioned the active galactic nuclei, and you mentioned 3C something. So these are quasars, Now quasars are billions of light years away. So you mentioned that possibly EHT will be able to image those black holes, but they are much further away. But that would be great if you can do that, because they are cosmological objects very far away. Yeah.
Yeah, we observe them, but those far away ones, I don't think we can image the black hole at event horizon scales or the shadow. But probably we are just studying the jets at much smaller scale than what we have with like centimeter wavelength VLBI. Yeah.
Michael, any question?
Yeah, yes, another question from Hermes Francis. What programming language that involved in this observation?
Good question.
Depends on the stage, I suppose. So, of course, at the beginning, when people is getting data, we use a program that's called DFX that was developed by Alan Deller to be able to correlate the data, like getting data from different telescopes and put it together. And later on, we will be using either software called, we'll be using either HOPS or some software developed by MIT to be able to calibrate the data. Then we will transfer this either to CASA, another software, to really reduce analysis, finding out what would be the different phases and amplitudes, or even APES, which would be a different programming language, Astronomical Image Processing System, or Common Applications. What was the one for CASA, Kevin? Common Application Software?
Common Astronomy Software Application or something like that. Yeah.
And then, of course, once we have the images, there will be a lot of softwares for the simulations, software for analysis. And I think some of these softwares is going to be like, for the simulations could be, I don't know. Again, we are not the experts here, but I think it would be like a lot of Python, a lot of C++, and all these kind of softwares.
Okay, so another question.
Yeah, like CASA, especially some of the more modern software, like APES, some of these old software are all like Fortran or C-based, where some of the modern ones like CASA is Python-based. But Python-based tend to be slow as well. So some of the software that they're developing for the imaging and all this, for example, are using Python. But some of the newer ones, they're trying to go back to C++ and all this as well, because it's faster compared to Python, which can be slower. So yeah, but generally astronomers currently tend to use Python a lot if you're thinking of what programming language you want to learn to become an astronomer. At this point in time, of course, things change very fast in the computer world. But Python is the most popular one in astronomy now.
Okay, so another question from Yong-Sing Yap. There was a paper which came out a few days ago, seems to have stirred some commotion on Twitter among academics, claiming that their independent reconstruction of the EHT data of M87 doesn't match the EHT results. But that point source simulation would also yield rings ring light results. I don't know if Kevin or Carlos is involved in the image reconstruction, but is there any response from EHT about this?
Wait, Michael, allow me to ask you, before we answer it, is it published in a reputable research journal? Is just a simple journal you cannot trust? It must be in a reputable journal.
There's a link from archive.org. I didn't open it.
Yeah. Which the name of the journal? That's what we want to know. Because there are many journals. Yeah.
Actually, we are actually aware of this paper, actually. And so maybe I'll tell a bit of history. Right, actually, the author, Miyoshi, is it Miyoshi?
Yes, Makoyo Miyoshi. Yeah.
He's actually a very famous VLBI astronomer in Japan. Right, and he wrote one of the most famous VLBI papers, previously, measuring the black hole mass. Can people still hear me? I think I'm stuck.
Can you? I think connection lost.
Okay, now there was a problem.
Hello?
Yeah, can hear, but your face is frozen.
Yeah.
Kevin, are you still there?
Maybe Dr. Juan Carlos, you can make a comment.
Okay, so maybe I can make a comment, and if Kevin can still hear us, maybe he will add on this. Yeah, so we had a discussion on the Event Horizon Telescope about this paper, and so far what we see is this person is already well known in the community. But when we look at the paper, what you made is a very good question. If is this in a good journal? So far it's in archive. And if we are correct, we think they are going to publish this in Astrophysical journal, so that would be a good journal. But we have been going through the papers, and especially one of our collaborators, Kazunori Akiyama, already had comments before this paper. And they have already seen that there is a series of concerns or ideas that may not seem to be fitting properly with the general knowledge for the data reduction analysis. And there are other series of papers, not only this paper that's mentioned by Miyoshi, but I think there is a really like 3 or 4 independent papers that have gotten the publicly available data for M87. They have reduced this data independently by their own means. And there are already 3 or 4 papers independent to the EHT that have recovered the results from the EHT. So far it's EHT, 3 or 4 more independent groups that all of them agree with the image of the black hole. And so far, this is the only paper by Miyoshi et al. That seems not to agree with these techniques. And we think that there is something in the methodology that should be explored further for this paper. I don't know if Kevin wants to comment further on this.
Yeah, sorry, I got cut off, so I had to go out and log in again. So yeah, actually we've been aware of this since a few years ago when the M87 paper came out, that he had already was claiming this a few years ago, but the paper was never published. I think it was rejected by a few journals. But he has been presenting this in a few conferences in Japan and all these things, where there were EHT astronomers who countered all his arguments and all this, and his processing and all these kind of things at that time. But of course, at that time, the EHT didn't officially make a official response because his work was never officially published. But I heard that one of the authors announced on Twitter that was accepted for publication in Astrophysical journal. So, but of course, I'm not sure yet whether this is true or not. But yeah, I haven't looked at the latest version of the paper, but the original draft version that we saw from 3 years ago, you can see there are a lot of issues with the way he processed the data and things that they are clearly, I would say at that time the previous one that was clearly wrong and all these things. So I'm not sure about the latest version that was put on the archive. So I haven't read the latest version yet. But probably we'll look into that, and if it's really accepted for publication in a journal, the EHT will probably give an official response, probably with another paper to counter that. So I guess that's how science works, right? I mean, there will be criticisms, there will be people who will test your data and confirm or invalidate your results and things like that. And we, of course, will try to defend. If it's wrong, then we will try to correct it. But if we think we are still correct, we will need to defend it, through the proper channels, which is writing more papers to counter it and things like that. Yeah, but I've looked at the original version of paper, and there were a lot of issues because, like, one of the things he claimed is that because of the position of the telescopes, the coverage, right, of this, it tends to produce ring-like structures. But you can see our images of other targets like 3C279 and Centaurus A, which look like jets and have no rings in them, right? So that is one argument that is not true. And the other thing is because we also do like simulated images, right? We have simulated, synthetic images, fake images of different shapes, like disks or rings or double sources and point sources and things like that, where we run through the same algorithm, like the same processing and imaging techniques that we use for M87. And they don't produce rings as well. For those that are supposed to be double sources, our imaging techniques produce double sources. If they are point source, we produce a point source. If it's a disk, we produce a disk. His argument that our tendency is to produce ring-like images is not true, right? If you look at one of the M87 papers, yeah.
Okay.
So there are some of the arguments we have, but of course some of that is quite technical. So sorry about
Okay, so I think this is a follow-up question from the same Yongsheng Yap. But we do observe the Fermi and E Rosetta bubbles to be completely perpendicular to the disk, which has lately been somewhat proven to be caused by Sagittarius A star. Does it mean that the black hole should be edged on?
So Juan, you answer that, or? I think is your mic off? Or?
Oh yes, sorry, sorry, I forgot to turn off my microphone. I was I was basically saying that maybe for this one I'm probably not the best person to answer that. Is not really my expertise. And again, that's something that models are mentioning. So this is the most probability that may happen about the inclination, but we cannot ensure 100% that is going to be the case. But of course, if Kevin has something to add.
Yeah, I mean, that's definitely a good question, especially like for the Fermi bubbles. We see it kind of goes perpendicular to the axis of the Milky Way, right? But the thing is, there's also sometimes what we see in a lot of active galaxies as well, right? Some of the active galaxies, what's happening in the center is different from what's happening outside, right? Because sometimes in the center, the black hole may be oriented in a different way, and maybe the gas that is being pushed out by the jets or whatever near the black hole is going this way, right? But after a certain time, because there's so much gas, along the plane of the galaxy, some of this gas that is going out gets deflected in other directions, right? Because you want to go through the path of least resistance, right? So it probably is not surprising that the Fermi bubbles might actually go in the direction that is perpendicular to the plane of the Milky Way, because that's the path of least resistance. But what's happening in the middle, we might not know, right? And also, we have already seen a lot of evidence of active galactic nuclei where the jets actually change direction, and sometimes can be up to 90 degrees or even more. I don't know what's the values we have now. And that is because the spin axis of the black hole sometimes can change, and there's precession, there's things going on. And sometimes we have seen jets where the jets are going this way and suddenly they go in totally opposite, different directions, which tells us that somewhere, along the path, the jets change direction, either because the black holes the spin axis has changed, since in the last time, or or something has happened in the environment of the galaxy or something. We're not sure. So, but yeah, it's not unprecedented, and it can be explained essentially by these kind of things. Yeah, I mean, again, I like Juan, I'm also not an expert in this, but I think these are possibilities. Yeah.
Michael, any more questions?
Yeah, I think there's one last question we have. How can we join EHT or LHC team for research?
Good one. I like it.
at the moment, first thing, of course, you need a PhD in astrophysics. It really helps a lot if you are being trained in astronomy, especially in the field of VLBI. So there you are. There are many students that are doing their PhDs, and they just basically join the EHT because their supervisors are EHT members, and they just give some project that is directly related with the EHT itself. But typically the process goes like you have some expertise, you think you can contribute somehow to the EHT, so there will be a series of panel people in the EHT, like the board meeting, the board panel. This will be like maybe one person for each region around the world, and those will be the persons that you may ask to join. They may consider your application, and then there will be a board meeting where they will discuss these people are asking to join the EHT, those are the expertises, those are the ways they can contribute, shall we accept them or not, and eventually maybe a few months later you can join. And typically the process goes like once you join, you start contributing. After you have shown a certain level of contribution, then you start appearing as a proper collaborator and as a proper contributor to the Event Horizon Telescope. I don't know if I jumped some step, or I think this is basically how it works.
Yeah, maybe I'll just add that, of course, you don't have to be only in physics, because the EHT has a lot of engineers as well, and computer scientists and all this who, of course, do a lot of things like developing the software that we use,
Right.
or do the technical stuff in terms of instrumentation and all these kind of things. So if you are more interested in those kind of things, like developing telescopes and instrumentation or programming and those kind of stuff, yeah, those are very good, useful skills to have as well, in astronomy or astronomical instrumentation.
So like the idea would be like how you can contribute to the project, right?
Yeah, I think currently the people who provide who are in charge of electing members are the board members. So just now Juan Carlos showed a slide, right, of the board institutions of the EHT, and those board institutions are generally the institutions that contribute telescopes to the EHT. So they are responsible for operating all the EHT telescopes, and the board members from those institutions, because the EHT has a board, right, and they have a representative from each of the institutions. They are the ones responsible for electing and approving membership to the EHT. So usually, if you are working in institutions that are within this one, then you should be able to join the EHT as long as you show that you can contribute something to the team. Like for example, like Juan Carlos, because he's Universiti Malaya, so he's actually going through the East Asian Observatory. And the East Asian Observatory is an observatory that consists of a lot of the institutes from East Asia, but also recently Thailand just joined. And Malaysia is one of the considered as an observer in the East Asian Observatory. Observer status, that means you don't contribute any money to the East Asian Observatory, but you are allowed to use the facilities and telescopes of the East Asian Observatory. So Juan Carlos is joined as a member through this, and for me, of course, I'm joined through the Academia Sinica site. So yeah, if you are in any of these institutes, you can join the EHT through either of these. Yeah, board. Yeah, it's complicated thing. Like.
Any more, Michael?
No more.
Yeah. So I would like to thank what I call our two very inspiring speakers here, Dr. Kevin Koay, who is now in Taiwan, and Dr. Juan Carlos Algaba. All right, thank you very much. And I just want to add opinion by saying that actually this is a beginning for EHT research. We have only two images, more to come. So just the beginning, very exciting. You guys will be very busy and getting a lot of your students to help you, because we know that in 2016, first direct detection of gravitational wave. In 2016, now we have 90 over direct detection of gravitational wave. For black hole research, you have 2. In the months and years to come, I'm sure you have add more. So now I will see it. At my point of view, there's a race going on. Direct detection of gravitational wave, the 90, and EHT. So we hope the EHT number should increase more and more. More and more countries should join in. So very exciting. And both of them are based on general theory of relativity by Einstein. So Einstein wins again, all right? But this very, very fundamental work by Einstein on what we call black hole in the general theory of relativity. So thanks again to Dr. Kevin Koay and Dr. Juan Carlos. So if ever Dr. Juan Carlos or Kevin, you're back in Penang, you're pass by Penang, please let us know. We'll take you around Penang. It's not only durian. Penang in a small place, and Kevin can tell you all kinds of food, makan. I'm here 3 years in KL. I've tasted Malaysian food, KL food, southern Malaysia food. Come to try the north, all right? And then also, if we have time, we'd like to invite you to give the talks in USM and in the Penang Science Cluster and this Tech Dome Penang, all right? So thank you so much. So we hope you have more success in future, all right? In this, all right? So whenever we go anywhere, we'll tell the students in Penang to watch tonight's broadcast, archive broadcast, so that we know that our Malaysians are also involved in cutting-edge research. For example, first one, 2019 was Hafizah Noor Issa from UIAM, Islamic University, in University of Glasgow. She was in the team, the LIGO team, to detect direct detection. We're so happy. All right, we want to invite her to come to Penang also. So thank you very much again. So Kevin,
yeah, it's a pleasure.
You see you in Penang soon also. Right? Thanks again, and thanks to our host Michael Teo. Michael.
Well, thank you for the Astronomical Society of Penang for letting us this opportunity to discuss about our work and how Malaysia is doing in these projects.
Yeah.
A pleasure to be here.
Okay, thank you and all the best.
Thank you. Good night.
Thank you.